start this. I totally thought that you guys were going to stick it to the man and just hand one assignment in as a group.
That's next time.
Yeah, but now I gave you the idea, so. I know. It's like this, it's like, do I really want to work with the entire class? I don't know. It's tricky stuff. Tricky stuff. Oh, just some, the final exam schedule is posted. You guys saw that? Nice. So we're on the very first day, very first time slot. Lucky us.
Why was only the business classes? How many at night is there? Everyone else was either 9 or 1.
Oh, because the business courses, there's so many different sections. And so for room availability, usually they're at night. Yeah, because they have to be like all at the same time. For example, all the business math right at the same time. Same with calc, like whenever there's lots of sections, even at the different campuses, they all have to write at the same time. So that's probably why. And as soon as there's a night section, it has to be at night. So there's that too. All right. I also posted, I did something kind of crazy. I posted assignment 5 on Moodle, but it's a Moodle quiz because it's for exponents and logs, which is what we're going through now. And so with the Moodle quiz, you'll have unlimited attempts and it'll tell you that what the answers should have been afterwards. It'll pick your highest mark. So a lot of it is multiple choice. You can do it, but also really good to use for studying, right, for the test, which is kind of coming up soonish, right? And so assignment 5, assignment number 5 is a Moodle quiz. I don't know, have you guys done a lot of Moodle quizzes yet, or yeah, you guys are okay on that front? All right. Not that there's anything groundbreaking about them. Anyways, it's a Moodle quiz. Due November 5th, which is the day of our test, at 23:59. So essentially midnight, that's when I make all my things due. Try to do it beforehand. Here's some stats: unlimited attempts. And it picks the highest, picks your highest mark or your highest grade. Okay. So that way we don't have to worry about, you know, you handing something in and you don't have feedback or anything like that, right? So some of the questions you're able to do after today. Some of the questions you'll have to wait until next day, but then you'll be all good. Okay. And just as a note, the final exam is on December 7th, which is a Saturday. First day of exams at 9:30 to 12:30. For some reason, the weekend exams start a half hour later, so you can sleep in. I don't know, I guess.
And it's gonna lock the building.
Yeah, well, I don't know what the difference between 9 and 9:30 is, but anyways, that's whatever. All right. So those were my, we're split between 2 rooms. But I'm just going to force this all into H101. But I'll put a note and talk about it later. But H101, that's our room. Okay. All right. So 6.2 is on logs, so logarithmic functions. Today will be nice background noise for when you're studying for camp. Logarithmic functions. So we already saw exponential functions last day, and we kind of hinted at, well, they're one-to-one, and so they're invertible, and here we are at logs. So in section 6.1, we saw exponential functions. Exponential functions, which have the form f of x equals b to the x. And we saw that they are one-to-one, which means they are invertible. So now we will explore their inverses. We will explore their inverses. The logarithmic functions. Which we just call logs for short. For the exponential function, just as a quick definition, for the exponential function, function f of x equals b to the x, the inverse of f, so f to the negative 1 of x, is log base b of x. So is called the base b. So it's log, and then the subscript is the b, the base, and then of x. Is called the log base b, bless you, logarithmic function. And you're going to read it as log base b of x. We had a common exponent and a natural exponent, common being base 10 and natural being base e. Same thing for logs, right? And so the common logarithm, the common logarithm of a real number x is log base 10 of x, right? So you put a little 10 in the subscript, and is usually just written as the log of x, and is usually written just the log of x. I guess I should put a little kind of definition box around the definition of the log. So the common log, so if ever you see log of x, it's implied that it's log base 10. Okay. What's nice on your calculator is it actually gets you to specify both the base and the x, right? So you can actually just use your calculator for all of these. But we need to know the rules for working with logs, not just finding logs. Same thing with the natural logarithm. The natural logarithm. Sorry, logarithm of a real number x is log base e of x and is usually written ln of x. Right, or if you're me, I get sloppy and I just write it like, well, not sloppy, I just use the natural log a lot. In fact, in stats, if we say log, we mean the natural log, right? So just like how we use base E for some situations like growth, and base 10 for things like intensity, right? pH, earthquake sound, that kind of thing. In stats, we stick to base E, right? So for me, I work in base E. The natural log is the only log for me. Sounds like a poem. But anyways, so we'll look at different bases. All the rules apply to all the bases, so it doesn't actually matter.
What's that thing? The hx, and then what's that?
Oh, this is my.
No, the one right beside it.
Oh, this one?
Yeah, what is
That's my my ln, kind of like
ln?
quick,
Okay.
yeah. Just so you recognize it, because that's probably how I'll end up writing it. Because this looks like an H, even though it's ln. But yeah, the quick squiggle is probably how I'll end up writing it, just so you recognize it. Okay, so logs, right, are the inverse of exponents, and so are exponential functions, and so the properties, right, are essentially the same, just the inverse, right? The domain becomes the range becomes the domain, right? And you've got that printout that I gave you last day with the properties of logarithmic functions. I guess there's no front or back, but on the other side, right? So we were looking at the properties of exponential functions, but the properties of logs are all derived from the fact, that they are inverses. They are inverses of exponential functions. So I'll go steal this. Come on. Oh, okay. So, just to talk about them quickly, right? So remember the domain for an exponential function was from negative infinity to positive infinity. And then the range was from 0 to infinity, right? And then, so now we flip-flop those. So the domain of a log is from 0 to infinity, and the range is actually from negative infinity to positive infinity, right? So those flip-flop, but that's a property of the inverse, right? And then, so 1, 0 is on the graph, right? Before we had 0, 1, but that's okay, right? Again, it's the inverse. And x equals 0 is the vertical asymptote, right? We had a horizontal asymptote at y equals 0 before, but like I said, it's the inverse. So all of these properties are just linked up, right? F is 1 to 1, right? So the log is 1 to 1, and therefore invertible back to an exponential function. Nothing kind of crazy, but it is good to be able to recognize what a log function looks like. So log base b, as long as the b is greater than 1. Remember, the exponential function also behaves differently depending on if the base was larger than 1 or between 0 and 1, right? And so it behaves, so the log also behaves differently depending on what the base is. Right? Usually we're dealing with a b greater than 1, a base greater than 1. But if not, it kind of does a little switcheroo. Okay. So those are just good to go over and good to be able to recognize the graph, right, and kind of understand what it's going to look like. So logs undo exponential functions. So if we consider f of x equals 2 to the x, and if we say, okay, well, f of 3, let's have a look at f of 3. F of 3 just means that 2 to the power of 3, which we know is equal to 8. Therefore, the inverse needs to take a value of 8, so take an input of 8 and return 3, right? Because we gave it 3, so in the exponential function, we gave it 3 and it returned 8. So now the inverse, right, has to take 8 and give us 3. And in the beginning, change this to some weird shape. There. Take n. Right, so, oh, yeah. Oh, yeah. Yeah. You don't want those rays on your face. So the inverse needs to take an input of 8 and return an output of 3. For this first part, until we've developed real skills for solving these things, which we will, we're just going to do quick trial and error, but we're not going to spend a lot of time on it, okay? Because we know that the inverse of an exponential function, the inverse of f, must be log base 2 of x. So what we find is that the log base 2 of 8 must be 3, just by the rules, right? We need to have the same base. So we had 2 to the power of x was our exponential function, so it was base 2. So now we know that log base 2 of 8 must return 3. I was going to do some more kind of hokey pokey ones just to show you the behavior, but in the interest of time, I'm just going to say we will develop better ways to solve these problems. Better ways to solve these problems than trial and error. But we leave it at that for now. Right. Your guys' favorite thing, domains. Don't talk to me about domains. I know that's what you're thinking. So up until this point, right, we've had to keep an eye out for dividing by 0. We have to avoid that. And also taking the square root of a negative number, right? We can't do that. Now we're going to have another criteria to kind of look out for, right? And so up until this point, restrictions on the domains of functions came from 1, avoiding division by 0. Division by 0. It keeps like changing my pen. It's like I'm running out of ink, but that's impossible. And avoiding the square root. So avoiding square roots of negative numbers. With the introduction of logs, we also need to remember that the domain of f of x equals log base b of x, right? So the domain of a log is from 0 to infinity, right? So we can only handle x's between 0 and infinity, right? Not even inclusive of 0, right? If you try log of 0 on your calculator, it's going to give you an error of some sort. Okay. So the input which is x, right, of the log must be strictly positive. So this means that another restriction is that we can't take the log of 0 nor a negative number. That's even more than the square root condition, right? Where we can take the square root of 0, that's fine, right? But now we can't even take the log of 0 or a negative number. Right. So as a quick example, if we have to find the domain of a, if f of x is 2 log 3 minus x minus 1, the only problem that I see, so I don't see any division, so that's nice, right? So we don't have to worry about dividing by 0. There's no square roots, and so we don't have to worry about those. There's just that log, and so what we have to make sure is that this can't be 0 or negative. So we need 3 minus x to be greater than 0. And not including 0. We can math on inequalities, right? As long as we're not dividing by a negative number or multiplying by a negative number. No, it's just dividing, sorry. Then the sign switches. It's early for me too. So here, if we just add x to both sides, we get 3 is greater than or equal to x. Or I prefer to have x on the left because I need to know what to do with x, and so it's easier for me to read. But that's just me being, I guess, maybe a little bit weird. Because I want to say x has to be less than 3. I want to be able to read it that way. But again, that's just me. Or in interval notation, if x has to be less than 3, then it can take on values all the way from negative infinity to 3, but not including 3. All right, so round bracket. So we can check using Desmos if we want. Where is it? And what was our function? 2 times the log. What's nice about Desmos is it's clever enough to know that 2 log means 2 times the log. But if you go into your functions, and I think it's in miscellaneous, there it is, 2 log, and then of 3 minus x, close the bracket, and then minus 1. So here, the domain sure looks like it ends somewhere at x equals 3. It goes to 3 and undefined. It's not very helpful. So it kind of ends. It's just showing you that it ends there. So in Desmos, can't remember what it looked like. Almost crossing at 0. For my rendering, I think that's close enough. Right, at 3, that's where it ends. Oh. What if we had g of x is the log of x over x minus 1? Okay, so the natural log, sorry. So we need x over x minus 1 to be greater than 0. And on top of that, x minus 1 can't be 0, right? Because we can't divide by 0. So, and x minus 1 cannot be 0. Since x minus 1 can't be 0, right, then we know that x can't be 1. So that's our first guy on the chopping block. Is x can't be 1. Okay. We also know that we have to be greater than 0 but we know that we can't be 0, right? And so if x is 0, then we've got 0 divided by -1, which is 0, right? And so we can't have that either, right? So we also can't have x over x minus 1 equal to 0. So x can't equal 0. Oh. Okay. Right. I'm pulling out that 0 because what I need to do, right, is I need to figure out, so for what values is this x over x minus 1 going to be positive and negative, right? And so we're going to use a sign diagram with cutoff points at 0 and 1. And so we know x equals 0 and x equals 1 will be transition points. I guess I'll just say could be, but I know that they will be, but they could be, right? So that's why we're checking them. So we use a sign diagram to determine when x over x minus 1 will be positive and negative. So we have to put 0 and 1 on this timeline, right? Because those are transition points, potentially. Could just be that it's always negative. That's not going to be the case. But so then what I do is I pick a value, just any test value in each of these regions, right? Each of these 3 regions. And so here, I'm going to use -1/2. And then I'll try +1/2. And then here I'll try 2. Sick of fractions. Not that they're that bad in this case, but. What we do, right, is we say, okay, well, when x over x minus 1, if x is -1/2, I get -1/2. How about we just do 0.5? -0.5 over -0.5 minus 1, which is just going to be 1/3. You can use your calculator. It's just going to be -0.5 divided by bracket -0.5 minus 1, 1/3. So that's positive. You know what? I'm going to change this to 1/2. So now I've got 0.5 over 0.5 minus 1, which is -1, right? But 0.5 divided by, and then in brackets, 0.5 minus 1, I get -1. So up here, I've got a negative value. Decided to use different colors to try to highlight what I'm doing here. So when x is 2, right, we've got 2 over 2 minus 1. 2 over 1 is just 2. And so we're back to positive. So for this region, it's positive, right? The result is positive, and then between 0 and 1, it's negative. And then from 1 onwards, again, it's positive. Therefore, we know x over x minus 1 is greater than 0 on negative infinity up to 0, round bracket, right? Because it can't be 0, because that gives us 0, which is not in the domain, right, of the log. Union, we pick it right back up at 1, and we can go all the way to infinity. Nice. We can check it using Desmos. If we've got, what was our function? The natural log of x divided by x minus 1. And then close that bracket. Right, so it looks like we've got this, come on. This asymptote at 1 and then at 0, and there's a space in between, right? So it just confirms what we found. Okay. Any questions about that one? No. Okay. So let's keep talking about logs in 6.3, properties of logarithms. Some stuff we can actually use. So, see handout. But there is a little typo, or not a typo, it's a copy past the problem. So I'm going to copy this guy. The first one is fine. Oops. All right. So the inverse property of exponential and log functions, we've already figured this out, right? And we've seen it before, right? But here it is in print, I guess. B to the power of a is only c if and only if the log base b of c is equal to a, right? And then same thing here. The log base b of b to the x equals x, right? For all x, and b to the power of log base b of x equals x. We're going to use this fact if we have to, in that situation where we looked at, okay, well, something has to take 8 and return 3, right? Then we're going to be able to use this property to figure out, okay, well, if I need to rewrite a number, in a specific base, right? So I have to rewrite a number in a specific base. Well, that's going to be the log of that base, and then the base to the power of the number that I need it to be, right? So we'll use that in a little bit here. Okay. But besides that, nothing crazy here. The printout has theorem 6.4 twice. And the reason is really stupid because I went back and I changed it because the frame, when I copied it, the frame got cut off and I thought it looked ugly. So then I decided to change it, but I guess I copied the wrong one. So anyways, it should have 6.5, which is this one here. Oops. Copy. Keeps shoving the newest one to the top. There we go. Luckily, it's nothing groundbreaking. It's the one-to-one theorem, I guess we could call it, for one-to-one properties. So remember, to show if something's one-to-one, you show that f of a equals f of b means that a equals b. And so if you've got an exponential function, it just says that b to the power of u is only equal to b to the power of w if u equals w, right? So we've seen that property before, but here it is in terms of exponential functions. And same thing with logs. If log base b of u equals log base b of w, that's only true if u equals w, right? That's the only thing that's changing in there. So again, nothing revolutionary here, but just facts to have laying around in your brain. Oh. I'll just grab the other properties. But I know you guys are still maybe working on that one. The other ones, luckily, I got on there. Okay. So these algebraic properties are going to be really important for us to know just inside out, be very comfortable with working with the algebraic properties of logs and exponential functions. Okay. And so here they are. Sorry. Does anyone need this still? Am I going too fast? Yeah. Got that feeling. I was writing, and then as soon as I scroll, stop. Okay. So let's talk algebraic properties. So exponential functions and logs have slightly unique properties, right? Because if we're talking about the function of u plus w before, if it was just any function, then we said, well, we can write that as f of u plus f of w. But because we're dealing with exponential functions, right, b to the power of u plus w plus u becomes b times, or b to the u times b to the w, right? So it's just the behavior of exponential functions. And so if you're adding inside for the exponent, then you end up multiplying when you break it up. Same thing, u minus w, so f of u minus w, you've got f of u over f of w, right? Because you've got, if you break it up, you've got b to the u times b to the negative w, which you can write in the denominator, right? And then same thing for the power rule. Right, so I actually would just think about them this way. Right, I would just think about them because we know rules of exponents, right? And so these guys aren't that big of a stretch, right? We know if we have a negative exponent, then it goes in the denominator and things like that, right? And so I would just think of this turning into this instead of going and memorizing these functions, right? How they transform. Yeah. Today we're going to focus on logs, so that's why we'll come back to exponential functions next day, but for now we'll do logs. And so for logs, if you've got the log of u times w, then to break it up, you do the log of u plus the log of w, right? And so this is the property to keep in mind. Also, if you've got division inside of the log, then it breaks out to be the numerator, so the log of the numerator minus the log of the denominator. So if you're simplifying stuff, then these things come in handy. Here's potentially the most important log property that we have is that the log of u to the w, we can rewrite as w times the log of u, right? So essentially, if we take the log of the exponential function, it brings the exponent down in front, and that's how we're going to be able to solve for x, right? If we wrap a log around something with an exponent, then we're able to bring that exponent down and solve for it, right? So this is how we solve for exponents. This is how we will be able to solve for x when it is in the exponent. So then I kind of went old school and I wrote up the example in here just so that you have them. But let's go through and do them. Good enough. I didn't have lines, I guess, so it's kind of wonky. So expand the following using the properties of logs and simplify. Assume when necessary that all quantities represent positive real values, right? So we don't have to worry about the domains or anything like that. We're just expanding and simplifying these logs. So A, we've got log base 2 of 8 over x. Now you've got those properties handy, right? We've got 8 over x, which means we can rewrite this as the log base 2 of 8 minus the log base 2 of x. Here's where we get to take our calculator for a test run. Otherwise, you would have to imagine 2 to the power of what equals 8, which is fine, right? But your calculator can just do it for you. And so if you hit the log button, which is kind of on the right-hand side in the upper corner, I guess, it'll ask you for a log input, base 2 for us, and then use your arrows to move into the next empty spot. And we want 8. So log base 2 of 8 is going to be a number, and that number is 3. And then minus the log base 2 of x, there's nothing we can do there. Use calculator. Oh, is it letting you do? Oh, I think it's a log base 10. We can look at it later because I think it probably has it. It's just going to be a little different. Yeah. And so it's nice that these calculators can just use any log and we don't really have to think about them, right? So as soon as you have the log of a number, that is a number in itself, right? So we're able to solve for it. Any questions about that one?
Yeah, I was not sure. Do we just leave it like do not need to solve for x?
No, just expand and simplify. Yeah. So is it simpler? No, not really, but we're just applying properties of logs, I guess. That's what the question should have said. Manipulate using properties of logs. Oops. B was log base 0.1 of 10x squared. This would be one of those rare instances where you've got to be a base that's between 0 and 1, right? 0.1. All right. Inside the log, we've got 10 times x squared. So we've got multiplication, so we can expand this out. And we've got the log, the base stays the same, 0.1 of 10 plus the log of base 0.1 of x squared. We can take the log base 0.1 of x squared even further, right? And then we've got the log base 0.1 of 10 plus 2 times the log base 0.1 of x. Right, so that's where we're using that property that if you've got the log wrapped around it, then yeah, the power can be in the exponent or it can be out front multiplying.
Does it matter which one you want on like a test?
I want the power out front multiplying. Yeah. Just because it's simpler. And if you do log base 0.1 of 10 on your calculator, you'll find that it is -1, womp womp, plus 2 log base 0.1 of x. How about C? the natural log of 3 over e times t squared. Oh yeah, sorry. 2 questions. Yeah.
What happened to the x squared?
Oh, so here, remember that last property where if you have the log of a power, you can rewrite it as the power out in front?
Oh,
Right, so that's a powerful property, pun intended. Yes.
What are we doing?
What are we doing?
What are we solving for here?
So we're not solving anything. We're manipulating, just using properties of logs.
Is to express something in a different manner? or-
Yeah, so for you guys, you will be dealing with logs. There's no ifs, ands, or buts about it. And so you need to be really well versed in just being able to take an equation with logs and just manipulate it to something that you're able to solve.
So let me re-ask. So in what setting would I be using logs? I just can't like wrap my head around what to make of math this is applicable to or something that this is applicable.
pH, you need logs. Say what?
Well, in class for hydrology, we had to graph using log paper.
Yeah.
So
You guys will be using logs. I'm the theoretical side. So here's how logs behave, right? And so there definitely is a disconnect, right? Where I'm like, I don't actually know what you guys are going to be doing with them. I just know logs, right? But I know that you'll need logs. So, so this is probably the chapter that I'm like, no, this is important, right? The rest of the stuff I'm kind of like, whatever. But yeah, so you will need logs. And like I said, pH, which I'm assuming is a big deal for you guys, right? Definitely dealing with logs. So, but yeah, I know, weird, right? Right now though, we're just manipulating using logs, using the properties of logs. All right, so here we go again. We've got the natural log of 3 over et to the power of 2. Because we've got that log wrapped around, we can rewrite this as 2 times the log of 3 over e to the t. Right. Which is a lot easier to deal with. Right. Especially because now we can also break out the quotient or the division inside the log. So we've got 2, and then remember it's all times the log of 3 minus the log of e times t. I'll use big brackets, even though I didn't need them. E is a number, but t is the variable. So e is the 2.71728.
so when you brought the to the power 2 out front,
Yeah.
But isn't log like on its own? I thought it had enough.
So the log of something is a value, but log on its own is a function. Yeah, so it takes a value, but log on its own is not a function, unlike e, right? E is a number, but the log's not. Yeah, it's just that.
So like if the square were just on the e, you couldn't put it in front of everything.
That's right.
But because it's
Yeah, you're only allowed to do it if it's for all of it. Yeah. Mm-hmm. Yeah, and it's just a weird but handy property of logs. So now we can expand this even more, right? 2 times the log of 3 minus the log of e times the log of t, well, times t is the log of e plus the log of t. So many brackets. But you'll want to be careful, right? Because that negative is now on the log e and the log t. Right? And so we've got 2. If we kind of expand this now, we've got 2 times the log of 3 minus 2 times the log of e minus 2 times the log of t. The log of e is just 1. You can try it on your calculator, but it is 2 times the log of 3 minus 2 times 1. Log of e is 1. Because you're applying the inverse on e to the power of 1, which gives you x, which in this case is 1. Minus 2 log of t. 2 log 3, you can try it 2 times the log of 3. Doesn't give you a nice number, so I'm actually just going to leave it as 2 log 3. So which is 2 log 3 minus 2 log of t. I'll make a note here that it's not a nice number. So we will leave it. T. If we're taking the log, the common log, right? There's no base specified, so it's the common log, base 10, the cube root of 100x squared over y times, oops, my y turned into a rectangle. X, y times z to the power of 5. First thing I'm going to do is, because I'm taking the cube root, right, I can rewrite it as the fraction 100x squared over yz to the power of 5 to the power of 1 over 3, right? I can do that. So I can rewrite this as the log of 100x squared over yz to the power of 5 to the power of 1 over 3. Because now everything's to the power of 1 over 3. And like we just talked about, right, everything has to be to the power in order to bring it outside. So we can rewrite this as 1 over 3 times the, oops, there I go, ln, the log of 100x squared over y times z to the power of 5. Give myself some more room. I'm going to scoot over here. I will break up the fraction, right? Rewrite it as I'm subtracting logs, right? And just remember that the 1 over 3 is multiplying everything, right? And so I've got these clear outside brackets. And I'm going to start writing the log of 100x squared minus the log of y times z to the 5, end bracket. You've got two options. You could rewrite 100 as something to the power of 2. Or what I'm going to do, just play it safe, is because I'm multiplying inside, I'm going to split them up. And same with the yz to the 5. I'm going to split them up and just deal with them individually, because then I'll be able to bring those powers down. And so I've got 1 over 3 times the log, I'll do square brackets, the log of 100 plus the log of x squared, all minus the log of y plus the log of z to the power of 5. Now that x to the power of 2 and z to the power of 5 are alone, right? So everything inside the brackets are to the power of 2 and 5. Now I can bring those powers down in front. And so I can do 1 over 3, just depends on what order you want to go in, but here we go. The log of 100 plus 2 log x. And then I'm going to expand that negative into the brackets. So then I get minus log of y minus 5 log of z. Okay. The only one that's a number here is the natural log of 100. So I'm going to see if my calculator gives me anything nice. So log base 10 of 100 is 2. So we've got 1 over 3, still all times 2 plus 2 log x minus log y minus 5 log z. That's right. Yeah. Because in the original question, it was just log, no base. So it's the common log, base 10. Okay. All right. I guess we can bring the 1 over 3 inside. So if we're getting rid of all the brackets, 2 over 3 plus 2 over 3 log x minus 1 over 3 log y minus 5 over 3 log z. There, simplified. No, not really, but manipulated indeed. How about that last example where we had the log base 117, so weird, of x squared minus 4. Yeah, sorry, Chair.
Just on the last one there, you from adding the log to the power of 5 to 5 just on the last
From here to here?
Yeah.
Well, it's because I had minus the log of yz to the 5, right? So this minus is actually on both of these, right? And so that's why I wanted to wrap it up in brackets. But then I expanded that bracket. So now I've got negative log y and then negative 5 log z. So I did 2 steps in one there. There's no properties for dealing with x squared minus 4 in here, right? We only have properties for dealing with if we have something to the power of something, something to the power of something, right? Right, so we only have properties for dealing with exponents in there, multiplication and division, no addition or subtraction, right? And so there's nothing that we could really do Nothing we can do. Unless if you want, unless we factor, but it's not something that I would expect you to do. So if you write the log of base 117 of x squared minus 4, remember on that kind of, I guess it's a formula sheet, definitely. The most recent printout with the volumes that I gave you, right? You've got the factoring formulas, so x squared minus y squared. You can rewrite that as the log base 117 of x squared minus 2 squared. And then you can use the factoring formulas. I don't really see why, but it gets you to a point of x plus 2 times x minus 2. Right. Now you're multiplying, which you can rewrite as the log of base 117 of x plus 2 plus log base 117 of x minus 2. I don't really see why you would want to do that, but maybe there are scenarios where you do. And now you know. What if we had to go the other way, right? So if you flip your page, for example, 2, oh, I guess I'll steal it from the printout. Use the properties of logs to write the following as a single log. Right? Just going the other way. We can only combine logs if they have the same base, right? So luckily for us, log base 3 and log base 3, they're the same, so we're able to combine them, right? If they're subtracting logs, then that's the same as division inside our combined log. So if we have log base 3 of x minus 1 minus log base 3 of x plus 1, that's the same as log base 3 of x minus 1 over x plus 1. Nothing else we can do there. It's a single log. And I think the question did ask for as a single logarithm. Done. B, we've got the log of x plus 2 log of y minus the log of z. If we've got 2 log y, we can rewrite that, we can condense it as the log of y to the power of 2, right? We can bring that power back on top. So I think I'll need a little bit more room here. I've got the log of x plus the log of y to the power of 2 minus the log of z. It doesn't matter if you start with the multiplying or the dividing. I'm going to start with the multiplying, just move my way from left to right. And so log x plus the log of y squared becomes the log of xy squared minus the log of z. Which if we're simplifying to one log, we've got a log minus another log, so that becomes the log of xy squared over z. need big brackets.
You can do the square on the outside of the brackets, right? For the y.
Yes. Yeah, because it's only y inside. Right. But if I had a choice, I'd prefer it on the inside. Sometimes it'll be on the outside, but it should be on the inside.
Wouldn't it not matter if you had another variable on the inside? In front of the entire log, so it wouldn't matter. So you can still put it on the bracket. Like if you had y-axis would still be.
Yeah. I just like it on the inside.
So if we have multiple, you still want to use like y squared x squared, y-axis squared.
There, it doesn't matter. Yeah, just do what feels right. Okay, C, 4 log base 2 of x plus 3. 4 log base 2 of x plus 3. Well, the 4 log base 2 we can rewrite as log base 2 of x to the power of 4, right? It's the plus 3 that gives us grief. Because we want to write this as a single log, right? And so we need to write 3 as a log base 2. Need 3 as a log base 2. Maybe as a side note here, to rewrite 3 as a log base 2, we use the property that log base b of b to the x equals x. In this case, that x has to be 3. In this case, we need x equal to 3 and b equal to 2, right? We said we want log base 2. And so 3 becomes the log base 2 of, well, we know b, right? B is 2 to the power of x, which we said was 3. So 2 to the power of 3, which is 8. So 3 we can rewrite as log base 2 of 8. So then, just kind of picking up where we left off here, we've got log base 2 of x to the 4 plus log base 2 of 8. Which is log base 2 of x to the 4 times 8, but I prefer to write it as 8x to the 4, but that doesn't matter. A single log. Okay. How about D? D was the negative log of t minus 1/2. We're going to have to do the same thing with the minus 1/2, right? Rewrite 1/2 as a log base e. So this becomes the log of, so negative log t we can rewrite as the log of t to the negative 1, right? Minus 1/2. One half is the log, the natural log, which is base e, of the base, which is e to the power of 1/2, right? By that other property that we just mentioned. Right? Log base b of b to the x is x, right? So if we want x to be 1/2 and the base to be e, then the log base e of e to the power of 1/2 is 1/2. So we can rewrite 1/2 as the log of e to the 1/2. So we get the log of t to the negative 1 minus the log of e to the 1/2. E to the 1/2 is the square root of e. Which is the log of t to the negative 1 minus the log of the square root of e. We're subtracting, right? So it becomes a fraction. So we've got the natural log of t to the negative 1 over the square root of e. T to the negative 1 we can bring to the denominator, and so we've got the log of 1 over t times root e. But technically we were done at that earlier step. So we said earlier that we have to have the same base, right? And so in order to do these manipulations, we can only merge the same base. And so in order to do these manipulations, we must have the same base, which brings us to the change of base formula. The change of base formula says that a to the power of x, this is more for exponents, right? If I want to move from a base a to a base b, then I can rewrite it a to the x as b to the power of x times the log base b of a. Right? We'll use that one a little bit more later. But here, so log base a of x, we rewrite it as the log base b, our new base of x, over log base b of a, which is actually our old base. Right? And so this is just a formula, probably a good one to work with. So let's do an example. Example 3 is on your printout. Started small, but then it went huge. Or I went huge, maybe. I don't know. So use the appropriate change of base formula to convert the following expressions to ones with the indicated base. So if we want to convert, I'll deal with this page break here, a 3 to the power of 2 to base 10, right? We want to rewrite 3 to the power of 2 as something as 10 to the power of something. Right? not something. That didn't make sense. So we're going to use the first property, right? A to the power of x is b to the power of x log base b of a, and see where that gets us. So we've got a to the power of x, because that's what our first one looks like, 3 to the power of 2, is b to the power of x log base b of a. So we've got a equal to 3, x equal to 2, a equals 3, x equals 2, and b equals 10. Is 10 to the power of x, which is 2 log base 10 of 3. Two log base 10 of 3 is likely going to be pretty nasty, so I'm just going to leave it as that. But 2 times the log base 10 of 3, yeah, no. Just going to leave it as that, the exact number. B, if we want to convert something like 2 to the power of x to base e, same idea, right? We've got the original base, a is 2, x is x, and the new base is e. So I always start with the formula and the property, right? The bare bones. So a to the x is b to the power of x log base b of a. A is 2, x is x, b is e, x is x log base e of 2. The only simplification would be rewriting log base e as ln, right, the natural log. So 2 to the power of x is e to the power of x log 2. How about C? I'm going to change a pace. C was the log base 4 of 5 to base E. More applicable, right? Because if we're manipulating logs like we were earlier, and we need them to have the same base, then we need this change of base formula. Okay. So what we're going to do is we're going to use the change of base formula, which is that log a of x is log base b of x over log base b of a. So log base, I said it, forget it. Log base a of x is log base b of x over log base b of a, where b is, of course, our new base still. And a is our old base. So a equals 4, x equals 5, and e is our b. B equals e. So then log base 4 of 5, we can rewrite as log base e of 5 over the log base e of 4. log base e, I'm going to rewrite as the log of 5 over the log of 4. Oops, but I wrote 5 again. Yeah.
Would log 5 over 4 be something different?
That's right. Yeah, so you want to be careful because you can't just smush these logs together because they're each functions. But yeah, good call. Okay. How about the last one? The log of x, change it to base 10. So again, I'm going to start and identify what's what here. A is base e, right? The original base is base e. X is x, and my new base is 10. And so I've got the log base a of x is the log base b of x over the log base b of a, which is the log base, oh, I'll start on the left-hand side, sorry, the log base e of x. Just writing it in that same format, but it doesn't matter. Log base 10 of x, because x is x, over the log base 10 of e. Log base 10 we can just rewrite as the log of x over the log of e. But it's simplified at the log base 10 stage. Okay. There's also just the special case, right? Conversion to the natural base. Which we just saw, sort of, earlier. For converting to or from the natural base, we can use these formulas, but I like to stick with just the default ones and apply it with the natural base. We don't actually need these ones. Okay. How about we get started on 6.4 because it's too much to just leave. I know. 6.4, we're moving on to exponential functions. Nothing crazy, but equations and inequalities involving exponential functions. So what we've been saying is that we need some better technique, or techniques for solving for x in something like 2 to the power of x is 129, for example. You could trial and error it, but that's going to be really hard. You could use the inverse properties. So we could use the inverse properties which says that we can rewrite 129 as 2 to the power of log base 2 of 129, which is 2 to the x. Which means that x is going to be log base 2 of 129. As you can sense, there's definitely a better way than using the inverse property. So, but the following method will prove more efficient. To bring x down from the exponent, isolate the exponent inside the log, or sorry, no, I got ahead of myself. Not inside the log. We're not there yet. Isolate the exponent and take the log we will use the natural log. It's common practice. But any log will do. Do log base 41 if you want, but it's harder. Not on your calculator, so it just does it. So it doesn't matter. But we'll use the natural log, so, and take the log of both sides of the equation. So what does that look like? If we have 2 to the power of x is 129, I've got 2 to the power of x. That's the only thing that's got the power on it, right, 2. And so I can take the log of 2 to the power of x is the log of 129. Don't forget to take the log of both sides, right? Like anything, if we have an equation, we have to do it to both sides. The log of 2 to the power of x, I can rewrite as x times the log of 2, which is the log of 129. Now I can easily solve for x, because x is going to be the log of 129 divided by the log of 2. Example 1, solve the following. A 2 to the power of 3x is 16 to the power of 1 minus x. First thing you want to make sure is that those powers are the only thing that's on there, right? So when we take the log, we're not bringing down the power in front of something that shouldn't have a power in front of it. In this case, it's fine. We take the log of 2 to the 3x is the log of 16 to the 1 minus x. We can rewrite this as 3x times log of 2 is 1 minus x times the log of 16, right? Handy dandy property. Solving for x, right? Now I need to just bring x's over to one side, everything else to the other side, and then I'm done, right? So I'm not going to do anything with 3x log 2, but I am going to expand on the other side to get the log of 16 minus x times the log of 16. Now, if I bring my x's to the left-hand side, let's say, I get 3x log of 2 plus x times the log of 16 is the log of 16. I can pull out a common x. So I get x times 3 times the log of 2 plus the log of 16 is the log of 16. So x then must be the log of 16 over 3 times the log of 2 plus the log of 16. And as long as you don't lose any decimal places, right, you can use your calculator. So the log of 16 divided by, and then I'm going to put everything else in brackets just to make sure that it's dividing all of it. So divided by 3 times the log of 2 plus the log of 16, and I get 4 over 7. A beautiful 4 over 7. And we'll do the next one as review next day. How about? Any questions? So many logs, exponents, so much fun.
So for that third line there, did you just not multiply the x back in then? You just left it as minus x log 16?
Yeah, this one?
Yeah.
I brought it over here. So I had to add x log 16 to both sides. And then I pulled out the common x to try to solve for x. Good luck on your chem today.